Namaskara. We will continue our discussions on great algorithms that are designed based on greedy strategy. Now we will look at a graph algorithm. We will discuss about minimum spanning tree or minimum cost spanning tree. So here G is a graph with vertex set V and edge set E. We assume that you have n vertices and m edges. We also assume that there is a weight function W. This is an arbitrary integer. It could be positive, negative, 0, it does not matter. All I want is this as an integer, that is it. It is not a big restriction, but we will assume that. We assume that the G is a connected graph. A tree T is a spanning tree, a T with the same vertex set and edge set E dash is a spanning tree for G if E dash is a subset of E. Notice that vertex set is same, edge set is a subset, and every spanning tree with n nodes will have exactly n minus 1 edges. Cardinality of E dash is n minus 1. Every tree. Spanning means all vertices are covered. Tree means it provides connectivity and there is no redundancy, no cycles. It is a connected acyclic graph. If T should be connected, obviously G must be connected. That is why we make this assumption. Otherwise we have to work in individual connected components, but we will assume that G is connected. Cost of a spanning tree is sum of the weights of the edges found in the tree. All edges, there are n minus 1 edges, each edge will have a cost according to this cost function. This is called the cost function or a weight function. We are interested in the spanning tree with minimum cost, okay. Find a spanning tree with minimum cost. So here is a very simple algorithm, remarkable algorithm. It is going to take you across a broad spectrum of computer science related discussions, ideas and techniques, the deeper mathematics and so on. Okay. So here is a very simple algorithm. It is a greedy algorithm. Try to accommodate as many cheap edges are possible. Okay. Therefore, you are going to consider the edges in the increasing order. So let L be list of all edges of G in increasing order of cost or weight. Cost or weight. Therefore, we are going to examine L in that order, because from the cheapest to costliest it goes. I will try to accommodate as many as possible. Okay. So, when do I ignore, when do I consider? That is a question to be answered. Our logic is also simple. A tree is a connected acyclic graph. So, if an edge is going to form the cycle, ignore it, because you cannot have a set of edges and one more edge and they would form a cycle. That will not be a part of the tree, right. Cycle can never be a part of a tree. So, let us say suppose these are the weights of the graph, weights of the edges of the graph. Now, consider this one, the graph with no edges, vertex set is seen. So, I will first start with n isolated vertices. Now, I am going to add edges. How do I add edge? I consider the minimum weight edge and see whether I can add. So, minimum weight edge is 5, this you can add. Minimum weight edge is 6, this also I can add. 7, there is a problem. If you add 7, a cycle is formed. If you add, and that is why I put in a spotted line. If you add that, it will form a cycle. So, I ignore it. 7 is cheaper, but I cannot construct that. Then 8, 9, this I will build. I have built 5 and 6 and then 9. Then 11, this is 11, this is 12, 9, 11, 12, 13, forms a cycle, I ignore it. 14 forms a cycle, I ignore it. 15 forms a cycle, I ignore them. So, finally 5, 6, 12, 11, 9. The total weight is 43, and this is the spanning tree. All vertices are there, and then okay. So, this is the idea. I go greedily, I try to accommodate as many cheap edges as possible. 6 I could accommodate, 7 I cannot, although it is cheap, because I have selected already 5 and 6. With that, when you put 7, a cycle is formed. So, although it is cheaper than the next one, I have to ignore it and then go for the costlier one. 9 is okay, it is not forming a cycle, right. Therefore, here is the pseudocode. Kruskals minimum spanning tree. Input is G equal to V E W. That is all is the input. Output is a minimum spanning tree. Let's call this the A. So, step 1, L be the list of all edges arranged in increasing order. Arrange them in the increasing order. Let L be the list of all edges arranged in the increasing order. 2 A equal to empty. Initially, the spanning tree has got no edges. A is empty. Vertex set is there, but edge set is not. Okay. E equal to first item in the L. Three, while not end of file, while you are not or while not end of no file L. While not end of L, if E forms E does not form a cycle with edges in A, then A equal to A plus E. Afterwards, go to the next edge. If E forms a cycle, ignore it, go to the next edge. So, if this is the case, do this operation and go to the next edge, otherwise ignore this and go to the next edge, else you do nothing. The next step is E equal to next E L. In that list, you might have got first one, then go to the second box, then go to the third box. That is all. While not end of L, if E does not form a cycle with edges in A, then A equal to A. So, you are selecting some edges and ignoring some edges. What is the guarantee that? First of all, there is no guarantee by looking into that algorithm the edges that are selected form a tree. That itself is not clear. Okay? We do not know whether it is a tree or not. Some edges are collected. Okay, assuming that it is a tree, how do you know that it is a minimum spanning tree? There may be some other spanning tree with a cheaper cost. So, we need to argue that this is the set of edges collected in this way in A, okay, is a tree, okay, and so on. So, basically we have an acyclic structure, because if an edge is forming a cycle, it is ignored. Therefore, the set of edges that are collected under A does not contain any cycle. Okay? The edges in A do not form a cycle. Okay, do not form a cycle. we will take a closer look at this and then extend to the formal proof. In fact, we are going to show that this step is going to be done exactly n minus 1 times. Therefore, you select A contains only n minus edges. When the algorithm terminates, that is because you are including A only n minus 1 times. There are a lot of edges, there may be millions of edges, but most of them will be ignored. The one that you retain, A equal to in A you include, you are including E in A. They form a spanning tree, they form a minimum spanning tree. The edges in A do not form a cycle. Okay. Now, if edges in A do not form a connected, it is acyclic. If you show that it is connected, then it is a tree, because definition of tree is connected acyclic graph is a tree. A is acyclic, there is no cycle in it, because any edge that is forming a cycle is ignored. So, the set of edges that you have collected will never contain a cycle. Therefore, it is acyclic. How do I show that it is connected? Suppose it is disconnected, we will arrive at a contradiction. Suppose it is disconnected. So, I have several connected component, consider any two connected component. The original graph is the original graph is connected. Therefore, these connected components, they have some common edges, they have some internal edges here and internal, but they have this bridge, okay, connecting these edges. There are bridges. So, the edges, I mean the cheapest one in this you should include, you can't afford to ignore that, because that is not forming a cycle. Any crossing edge has a potential to get included. Suppose this is the set of edges that you have selected so far. Consider a minimum weight crossing edge. That is not going to form a cycle with the edges that you have already selected. Therefore, that can always be selected. Only thing is, it has to be of minimum weight, but that is what we are doing. We are considering in the increasing order of weight. So, whether it belongs to different component or not, if they are in the same component, that path and this one will form a cycle, you ignore. If they are in different component, you take the union of that, right. That is how it would work. Therefore, the edges in A do not form a cycle, and the cross edges, the minimum weight crossing edge can always be added, and that is a contradiction, because greedy algorithm finished means no more edges can be added, but now we are showing that if it were not connected, it can be added. Since that is not possible, it is connected acyclic graph, therefore it is a tree. There is another characterization, it is acyclic and has got exactly n minus 1 edges. Therefore, this must have been executed exactly n minus 1 times. Sometime 3 edges can get added, sometime after hundreds of edges nothing can get added, it depends. Therefore, this is the Kruskal's algorithm, very easy to understand and implement. Arrange the edges in the increasing order of their weight, accommodate as many low cost edges as possible. Therefore, you try to accommodate by considering the edges in the increasing order of their cost. So, the lowest cost you consider first, the next lowest next, and so on. Try to include all of them. When will you exclude? You are now at an edge which when you include it forms a cycle. Okay. It should not form a cycle. If it forms a cycle, we are ignoring it. So, there is a beautiful way in which to check whether it is going to form a cycle or not. Okay. A is a set of edges. E is an edge that is not in A. Will E form a cycle with edges in A? How do we answer this question? In our example, we have physically seen, I put a dotted line, hey, here you see the cycle and other things. You can't do that. In a computer program, you have to write it and then it has to decide. Will E form a cycle with edges in A or not? We are not interested actually in the cycle. We are interested in the yes or no answer, because whether we have to consider in A or ignore it, that is all. Else it will form a cycle, we do not want such an edge, so you are going to the next edge. Therefore, we want a Boolean answer. Now, that Boolean answer is given by the following characterization and basic structural property of graph. Okay. Now, A is a set of edges, so the graph VE may have several connected components. Why we are interested in connected component here? Suppose UV is an edge and P is a path from U to V. P is a path from U to V. This is P, this is edge UV. So, P plus UV is a cycle. Okay. Now, such a path should exist in A. If that is the case, then adding UV to A will form a cycle. That means this path being providing the connectivity, all the vertices and edges must be in the same component. Okay? All paths, the entire path, it must be in the same component. In that case, it will cause a cycle. That is, let A1, A2, AT be the connected component induced by A. Suppose A is defining the connected component. Okay. If UV is an edge and U and V are in the same connected component of same connected component of TA. Both vertices are in the same component. So, what do you mean by a connected component? Every pair of vertices there is a path connecting them, that is a connected component. Okay, that is connected component. Because U and V are in the same connected component, okay, it is like this. This is the connected component, this is U and this is V, there is a path and this edge. Then UV will form a cycle. In fact, this is the reason why this edge would be ignored, right, because it is forming a cycle. But if U and V are in different connected component, so this is one connected component, this is another. If this is U and this is V, this edge in fact will fuse these two connected components, it will merge these two connected components and create a bigger connected, and there is no cycle that will be formed. Therefore, this will be included to A. Okay? So, this is going to be added to A. So, we now know when we can include an edge in A and when it is not to be included in A. Okay? So, let us put that in a little more formal way. Okay? Probably you can recall from your discrete math course, okay, a relation on a set S. What is a relation on a set S? Relation R is a subset of S cross S. R is symmetric if x y belongs to R implies y x belongs to. If x y is there, y x is also there. R is reflexive if x x belongs to R. R is a transitive if x y belongs to R and y z belongs to R implies x z belongs to R. This is transitive. If I have x to y and y to z, there is a x is a pair is also there. Now consider okay. Now the core theorem, basic theorem is every equivalence class so what is an equivalence class? Every equivalence relation. What is an equivalence relation? A relation is an equivalence relation if and only if it is reflexive, symmetric and transitive. This is the definition of equivalence relation. Okay, all the properties when you have the relation R is called an equivalence. Every equivalence relation induces a partition on the underlying set. That is, let R be an equivalence relation on S, then R defines a partition of S. So, what do you mean by a partition? Partition means, what is a K partition? A collection of subsets. S1, S2, Sk, such that union I equal to 1 to k of Si is S, and Si intersection Sj equal to Mt if I is. That is partition. Partition is a splitting a set into disjoint part. So, S1, S2, they are all disjoint part because Si intersection. This is the definition of a partition. So, the equivalence relation R, if this is a set, R is going to split into a partition, split into several subsets, and this is a partition. Now, consider a graph G with vertex set V, edge set E. Say a vertex U is related to vertex V if and only if there is a path from U to V. There is a relation. U is related to V, that is UV belongs to R, which is a subset of V cross V. UV is an element of V cross V. Here I define a relation. This relation is reflexive. There is a path from U to U. Okay. It is symmetric. It is an undirected graph. If there is a path from U to V, the same path can be considered as a path from V to U as well. Again, if you have a path from U to V and V to W, you can construct a path from U to W. Therefore, the relation U is related to if and only if there is a path from V to U is an equivalence relation. This equivalence relation is going to induce a partition on a vertex set. Those partitions are called connected components. The partition induced by the above relation is called connected components. So, all the things which are mutually related are put in one cluster. So, all these things are related and all these things are related and all this, but nothing is related between this and this. Okay. But within that all of them are related, it is a cluster. That is why it is called connected component. What is the property of a partition? Each set will have the defining property applied on all pairs of elements. So you take any two vertex here, there is a path. You to any vertex here, they have a path. You take any two vertex, but across there is no path. Alright, across there is no path. If you have several connected components. So here is a graph with the 3 components. So this has got 10 vertices, but it has got 3 different components. Okay, there are 3 different components. Each is connected, but so here is the here is the key point. Let A be the set of edges collected so far. Let E be the edge under consideration. Let E equal to UV. A induces a partition on V. Therefore, V is going to look like this. This is a set of all vertices. 2 scenario, U and V are in the same component. Then they are in the same component, they are already connected. Okay, then the path from U to V in the component and the edge UV and the edge UV form a cycle. That is the reason why if U and V are in the same component, the edge UV is ignored. If U and V are like this, the edge UV will never form a cycle with anybody. They are in different component. That is the reason why what we do is that, okay, let U V belong to E is under consideration. If U and V belong to same component, same connected component of A, then ignore UV. If U and V do not belong to same component, then UV does not form a cycle, hence include it in E. This is the crucial point. Okay? The crucial point is when we are including an edge and when we are excluding an edge. We have said if it forms a cycle you include, and if it is not forming a cycle, but how to determine whether it is going to form a cycle or not? That is a complex task. Instead, if we could answer this question, You have built A. A is a dynamic set. That A is going to induce a connected component. Whether it is joining two different connected components or whether they are the same. When you look at it, you will get an answer. With respect to this, we will take a look at the example. We will continue our discussion in the next session.